Hey folks, today I've got an example for you involving, or two examples for you involving free fall and multiple objects. Let me explain the picture for you that you can be copying down. Uh, there are two people, one's at the ground, one's on top of a building. They're separated by a distance h. And the person at the bottom is going to throw their book upward with an initial velocity of v naught a, and the person at the top of the building is going to throw their book downward with an initial velocity v naught b. Okay, and what we're going to determine is we're going to determine where or when and where they meet the books in terms of the givens and fundamental constants, meaning there will not be any numbers in our answers. Now, later on, I'll throw some numbers in, but right now, we're going to determine when and where the books meet in terms of the givens and fundamental constants. Now, if you need a sec to pause the video, now would be a good time. All right, so hopefully you have that picture copied. So what are the givens? Well, we were given V naught A, we were given V naught B, we were given the height, the separation distance, and that's the only three givens. And what's the fundamental constants that we might be using here? Well, we got free fall going on, so we're going to have G. Okay, now we know the value of G is about 9.8 here on Earth, but we're not going to use that. We're just going to say G in our equations. Okay. Now, in order to figure out when and where they meet in terms of those letters, by the way, first of all, normally in a regular class right now, I would pause and ask the students to give this a shot. So I would recommend that. I would recommend trying to write a few things down and see if you could figure out when and where they meet in terms of those four letters. I'll even give you a hint. When you find when they meet, the time, you're going to use only three of those four letters. One of them will be gone from the equation. So if you got a few minutes, that would be an awesome idea to give that a shot. All right. I hope you gave that a shot and you got some ideas about maybe how to solve this. There are multiple ways you could solve this. I'm just going to do one way that I think is fairly convenient. So what I'm going to do is I'm going to write the position of each book as a function of time. Okay. So a couple things to note here. G is defined as the value of G. If I see G in an equation, that just means 9.8. So if I want the acceleration to be negative 9.8, I got to throw a negative sign in front of it. Also, V naught B and V naught A, these are both positive numbers. If I want to express one of them in a negative direction, I have to slap a negative in front of it as well. So like maybe V naught A is 50 and V naught B is 30 or something like that. If I want V naught B to be negative, then I got to put a negative in front of it in the equation. Having said that, I'm going to define up as positive, and also I'm going to define the ground as zero height, okay, or zero position. All right, so let's start with A. If I write A, the position of A is a function of time. Y sub A is equal to, I'm going to use the equation, I'll write this down to the side. I'm going to use Y equals Y naught plus V naught T plus 1/2 AT squared. So that's the equation I'm using for all these. So Y of A, well, it starts on the ground, so there's a zero here, plus V naught, which is V naught A times time, plus 1/2. Now, the book, once I've released it, gravity is pointing down. So in my coordinate system, I've made up as positive. So I got to put a negative G in front of this for this to work. And then I've got T squared. And then I'll just tie this up ever so slightly. We got YA equals V naught AT minus 1/2 GT squared. So that is the position of book A as a function of time. I'm going to do the same thing for book B. Y sub B equals, now it does start with an initial height of H, okay, plus V naught B. Now V naught B is down, which is negative in our system. So I got to throw a negative in here. V naught BT, okay, plus 1/2. And the acceleration of the book is still down, so I got to put a negative in front of my G as well, just like in the previous problem. And there you go. And again, I'll tie this up ever so slightly. Y sub B equals H minus V naught B T minus 1/2 GT squared. All right. When the books meet, what do I know? Well, I know that their positions, y sub a and y sub b, they've got to be the same. So I am going to set these two equations equal to each other. So v naught a times t minus 1/2 gt squared, that's the ya, has to equal y sub b, which is h minus v naught b t minus 1/2 gt squared. And what I'm going to do in this equation is just solve for time. Now, thankfully, the negative 1/2 gt squareds cancel out. And if I put my v naught, or my vt terms on one side, I got v naught a t plus v naught bt. If I solve for t, the time in terms of the givens and fundamental constants is h over v naught a plus v naught b. Okay. Notice that G cancels out. This would work the same on the moon or on Earth. Doesn't really matter what G is. Basically because one book is slowing down and one book is speeding up at the same rate, so that kind of cancels out. Okay. Now, if I wanted to find where they meet in terms of the givens and fundamental constants, what I would do is take this time and plug it back into either of my y equations. So I would plug this back into, let's say, that one. It's a little easier. Now, I'm not going to do that. But if you wanted to, you could plug in t in there, and you'd have to FOIL some stuff out, and you'd get an expression for y where they meet as functions of the givens and fundamental constants. Okay. In other words, in these equations, you have to get rid of time because time wasn't a given. Okay. Now, just for kicks, we're going to throw some numbers in on this. So let's say that the height was 100 meters. Let's say v naught a was 80 meters per second. And let's say v naught b was 20 meters per second. Okay, well, our time would be, well, that'd be really simple. It'd be 100 over 80 plus 20, which would be 1 second. Okay. And then if I plug that back into this red equation up here, you would get y sub a, which has to equal y sub b, would equal 80 times that 1 second minus 1/2 times 9.8 times 1 squared. And they would meet at 75.1 meters up off the ground. Okay. All right, so that was example one. Now I've got a second example, which will be significantly shorter, is it's similar to this, but there you go. So I wrote each position as a function of time for each book, and then I figured that I had to make those equal in order to figure out when and where they meet. Now, the second example I have for you guys, again, it's very similar, but there are some differences. Let's say we have our building again, and I'm going to go back to letters now. So it's got a height h. Let's say person B up here. Now this time person B, when they let their book go, they're releasing it from rest. So V naught's 0. And here's person A, okay? And they're going to throw their book up with some V naught, okay? And here's a different question for you. How fast does person A have to throw their book such that the two books meet 3/4 the way up? Okay, so what's V naught got to be in order for person A's book to be 3/4 the way up when it strikes person B's book? Okay, so I'm looking again for what's V naught in terms of the givens and fundamental constants. Okay, so I'm going to start off the same way I did before. I'm going to write each position of each book as functions of time. So y sub a would equal, well, it starts at 0 height. Oh, by the way, I'm going to call this 0 height again, and I'm going to make up positive again. Plus v naught t plus 1/2. Acceleration is down, so it's negative g t squared. Y sub b, okay, well, that book starts a height h above the ground. It's not moving to begin with, so that's 0t plus 1/2. It's still accelerating down, so I got negative g t squared. Okay. Now, something else that's important here. I do know these are going to be equal when they collide. However, I've got something else that we know too. I know that y sub a is going to equal the position at B, and we've already said what it's going to equal. It's going to be 3/4 of the height. Okay, so what I'm going to do is for YA and for YB, I'm going to sub in 3/4 H. Okay, so in the Y equation, we've got 3/4 H equals, I'm going to get rid of 0. We got V naught T minus 1/2 GT squared. Okay, in the B equation, we've got 3/4 H equals H plus 0, so I'm going to not worry about writing that down, minus 1/2 GT squared. Okay, so that's the B equation. I'll kind of mark these. This was A and this was B. All right, so in the B equation, I am going to solve for time. Okay, if I subtract H from both sides, I get negative 1/4 H equals negative 1/2 GT squared. And if I solve for T squared, I'll just leave it that way, I get H over 2G. Okay, so T would be root H over 2G. Now I'm going to take that and plug that back into the A equation, and that will give me V naught. Okay, so I got 3/4 H equals V naught times T, which would be the square root of H over 2G. Okay, minus, now here's the cool part. I know that negative 1/2 GT squared is negative 1/4 H. So I'm just going to write that in. Here's my 1/4 H. Okay. My negative 1/2 GT squared is negative 1/4 H. All right. If I add 1/4 H to both sides, I get H equals V naught square root of H over 2G. And so V naught equals H times the square root of 2G over H. And if I simplify that out, I get root 2GH. Okay. Now, a reminder, if this were, let's say, the previous problem where H were 100 meters, G is defined as, in an equation, if I just see G, that's defined as 9.8. There's no negative in front of it. So this would be 2 times 9.8 times whatever H is, like in the previous problem, it was 100. Okay. And this would tell you how fast you'd have to throw your book in order for the two books to meet 3/4 the way up. All right, I hope those two examples were helpful, and thank you very much.